Assalamualaikum warahmatullahi wabarakatuh and good day to all students. Okay, now let's look at our example 2, double lap joint. Okay, in this case there are two shear interfaces and 4 20mm diameter bolt, which is grade 8.8 ordinary bolts. The outer plates are 8mm thick, while the inner plate is 12mm thick. All are S275 steel. Determined A and B as in the previous examples. So for you to do these examples, you need to refer the notes that has been uploaded to you, which is example 1. Okay, so A and B is, you need to check the minimum and maximum H and N distances, and also check the load capacity of the connection with respect to all this. Okay, before we continue, I would like you to watch the video that related to this double leg joint.
Shear strength is an important mechanical characteristic of a threaded fastener. It is a fastener's ability to withstand loads applied at a right angle to their bolt axis. A single shear will cut a fastener in half along one transverse plane. A double shear cuts the fasteners into 3 pieces along 2 transverse planes. The ASTM and the ISO have different standards for measuring shear strength. We will use a generic formula and approximate material values for this demonstration. Here's our fastener. It is made of low-carbon steel and has an ultimate tensile strength of 440 megapascals and a tensile yield strength of 370 megapascals. We can use these formulas to approximate what our ultimate shear strength and our shear yield strength are. Next, we will put our fastener into a double shear pin joint and mark where the 2 shear planes are. The shear force, or the load at each end, is 500 newtons. Since there are 2 shear planes, the load is distributed between them. Each shear plane experiences a shear force of 250 newtons. Next, we will calculate the area of the shear planes. Since the bolt is a cylinder, the shear planes will be circles. We could use the formula pi divided by 4 times the diameter squared, which gives us an area of 78.54 millimeters squared. Next, we can calculate the shear stress at each plane by dividing the shear force by the shear area. In this example, the shear stress is 3.183 megapascals. Our fastener's shear yield strength is over 65 times the shear stress it will experience from a load of 500 newtons. These photos from a NASA study display 2 more variables. The threads of a fastener have a smaller shear plane area and will break under weaker loads, and that the changing of the shear angle to less than 90 degrees creates a larger shear area and increases the load that the fasteners broke at. All this proves how important it is to understand the forces which your fasteners will have to withstand during their use. We hope you learned something helpful from this video. If you did, please subscribe and enable alerts so you can catch the next video we upload. Have a wonderful day.
Okay, in these examples, you can see there are 2 shear interfaces between the bolts. Okay, so the first shear interface will occur at this point, and the second one at this line. So you have 4 numbers of 20 mm diameter bolts and 2 rows shear, as you can see here. And this is the dimensions of the bolt. So as 150 kilonewton is pulling in these directions, and therefore it's balanced with 75 kilonewtons for each plate in the other directions. and this represents as what you see in the animations video of the double lap joint just now. So let's look at the solutions. The first questions in this example is for you to determine whether the given arrangement of bolts has exceed the minimum and maximum H and N distances or not. So if you look, you need to refer to this clause. You look at this table. Okay, so in these tables you have to make sure that the bolt diameter is within the specific recommendations given in the clause. Okay, let's now look at the solutions. So for bolt diameter, which is 20 mm, so it means that D naught is equivalent to 20 plus 2, whereby 2 mm is the clearance given the clearance of the 20 mm diameter holes. So in total it is 22 millimeter diameter. So given that minimum and maximum H and H distances, minimum and H distances is referred to table, which is 1.2 D naught. So therefore you calculate 1.2 times 22, you get 26.44 millimeter. So here, okay, maximum H and H distance, assuming still exposed to the weather or other corrosive influences. So for the maximum N distance, looking to the table, refer to the given table, which is 40 plus 40 mm, equivalent to 4 times 8, which is the thickness of the plate, is 8 mm, plus 40, which is 72 mm. Okay, so you are taking into considerations the least thickness. As you can see here, you have 8, 12 and 8 mm, so the thickness is 8 mm. So thus you can conclude that the E1, okay, is larger than 26.4 but lesser than 72, which is okay, and E2 is larger than 26.4, less than 72, which is considered okay. In terms of the minimum and maximum N and H distances, the proposed arrangement for these connections is satisfied. Okay, so now let's look at the table. We need to check for the bolt spacing, which is pitch distance, where we recognize as P1. So you can see in this table the requirement minimum and maximum spacing for bolt is given as these two columns. Alright, now let's go back to these examples. So you can see that minimum bolt spacing for P1, referring to the table, okay, in the Eurocode, you can see it is 2.2 D naught, whereby 2.2 times 22 is 48.4 millimeter. And the maximum bolt spacing for P1 is either minimum 14T or 200 millimeter. So now you have to choose, is that 14T or 200, whichever is give you the minimum value, and that would be the maximum bolt spacing for P1. So in this case the thickness is 8, okay, we choose the least thickness, and 200. 14 times 8 is given as like 112 millimeter. So 112 and 200 mm the resultant of 14 times 8, which is 112, is the lesser. Therefore, you get 112 millimeter. Thus, P1, okay, the bolt spacing, which is larger than 48.4 and less than 112 millimeter, and we consider it as okay. Okay, next, let's look at the requirement for P2. Okay, minimum bolt spacing for P2, which is equivalent to 2.4 D naught. Okay, so D naught here is calculated as 22, and you can see when you calculate you get 52.8 millimeter. So minimum bolt spacing P2, you need to refer to the table, as you can see in this table. So this is the requirement, and we are looking at this column. Okay, so that's why we have 2.4 D naught, which is 52.8 millimeter. And for the maximum bolt spacing for P2, we still looking at the same table, and it gives us this column. So from that table, we can see that the maximum bolt spacing for P2 is the minimum value, either 14T or 200 millimeter, and in this case we have 112 is the minimum, and therefore you can conclude that, okay, P2 is lesser than 52.8. okay, not okay, need to increase spacing P2 to minimum 53 millimeter. Alright, this is because if you look here, minimum bolt spacing is 52.8 and the maximum bolt spacing is 112, and P2 must less than 52.8. But if you look at your arrangement, P2 is 50 millimeter, which is less than the allowable minimum we have calculated earlier, and therefore we need to increase the arrangement of P2. Instead of 50, we need to increase up to 53 millimeter. So it means that you need to change the structural arrangement of the bolt. Okay, so now checking for question 1A, which is to check the arrangement of the bolt, whether it is within the requirement given, has already been conducted, and we found out that what we can conclude, okay, the P1, okay, is in the range of the suggested allowable given in Eurocode, where the limit of P1 is larger than 48.4 and less than 112, which is considered okay. And meanwhile, for the E value, okay, E1 and E2, okay, is also considered okay because it is within the 26.4 and lesser than 722 mm. However, in these examples, for the first questions, we just found out that the minimum requirement for P2 is not enough for the arrangement that we propose. So therefore, we need to increase the P2 to at least minimum 53 millimeter. Okay, now let's go for the first check in question 1B, whereby you need to determine whether the shear capacity of the connection can resist the bolt shear or not. Okay, so what I'm trying to say here, you need to make sure that the bolts, okay, you need to make sure that the bolts, okay, the bolts are not fail due to shear. let's look at this example. So let's look at this animation where how does the bolt feels in shear. Okay, haven't seen the animations video. Therefore, in the first objective for the second question, we must to make sure that the bolt that we are designing now will not fail due to shear, meaning that we don't want to have the bolt to fail whereby it is split up at this particular point where it at its shear line. To do so, okay, so you need to refer to these equations where it is for the shear resistance of the bolt, and this equation you can refer to this table. So in these examples, okay, the second questions, you need to refer to table 3.4 as you can see in this figure. So here in table 3.4, there are variety failure modes that must to be resisted by bolt. So you can see the first one, shear resistance per shear plane. So here we can see that there is a potential of the bolt to fail under shear. So in here you can see in this second column whereby FVRD is equivalent to alpha V FUB times A over gamma M2, where the meaning of this all parameter has been discussed or has been shown in this table. So our first task is to check that our bolt arrangement will not fail due to this shear mode. So applying these equations given in table 3.4, therefore you can see that here we have FVRD is equivalent to alpha B FUB AS over gamma M2. Alright, so here in this case where you can see alpha V is equivalent to 0.6 according to the table 3.4. Okay, because our bolt class is in the class of 4.6, 5.6 and 8.8. So therefore we need to use the alpha V equals to 0.6. Meanwhile, okay, for our FUB, okay, which is the ultimate resistance for bolts, so you can refer to table, okay, for tables of the bolt diameter, okay, where you can get a tensile or ultimate resistance of the bolts. So in this case you need to refer to this table. Okay, for FUB you can refer to table 3.1. alright, 3.1, where FYB for grade 8.8 bolt class is 640, whereby FUB is equivalent to 800. So for these two arrangement, okay, so therefore in these examples we then apply the value of bolt, which is 800, and then AS is 245. AS is represent the tensile area of your bolt. Where in this case you can refer to these notes, okay, or you can find the table specifications for bolts classes. So here you can see capacity of class 8.8 ordinary bolts, design grade S275 materials, and you need to find what is our bolt size here. So our bolt size is M20, so therefore the tensile stress area is given as 245. Therefore, in this case, that's why we consider in our examples, in our examples, AS is equivalent to 245 and gamma M2 is 1.25. So having that, you calculate, once you calculate it, you get 94 kilonewton. Since in this case, our plate or our bolt is experience 2 double shear. Therefore the shear value that you have, this is shear value per plane, and just to bear in mind, this equations is to calculate shear value per plane. So therefore you get 94 kilonewton per plane, and you have 2 double planes, therefore you need to multiply with 2 and you get 188 kilonewtons. So 188 kilonewtons, alright, should be larger than 150 kilonewton divided by 4, which is 37.5 kilonewton. And let me explain to you that. So in these examples, you can see there are 1 plane, 2 plane, 3 plane, and 4 plane. 4 plane, and then it is pulling by 150 kilonewtons. So 2 shear interfaces per bolt, meaning that one bolt you have 1 and 2. So when you have 2 bolts, 2 bolts, therefore you have 4 planes per row. Similarly for here, you have 4 planes per row. Therefore, in these examples, when you calculate here, when you calculate here, you calculate that each bolt will resist 94 kilonewton per plane. It means that for each plane, it will carry, the bolt need to able to resist 94 kilonewton. So but here we have to find what is the actual shear force that will gone through this plane. So we know that we have 150 kilonewton, and one bolts you have 2 planes, so per row of bolts you have 4 planes. So therefore, you need to divide by 150 over 4, so that you need to know what is the shear actual resistance that will pass through per plane, which is 37.5 kilonewton. In this case, since one bolt will have double shear, therefore 94 times 2, 188. So meaning that 188 kilonewton must be larger than 37.5 kilonewton. So you need to divide those 150 kilonewton to these 4 bolts, so that you can have what is the shear plane for each, what is the shear resistance for each bolt. So for the second questions, we are required to check the resistance of the given configurations to bolt bearing. So as has been explained earlier, bolt bearing is one of the mechanisms that can occur during these types of conditions, where when you pull the plate, each bolt will have a bolt bearing. So in this case, you can see in this case where you have to look at the table again. Look at the table. So in that table, in this table, you can see whereby for the bolt bearing, the bolt for each bolt, it has to able to resist the capacity for this bolt bearing resistance. You can see bearing resistance is given as FBRD equivalent to K1 alpha B FU dt over gamma M2, where all these parameters has been described in the following example, in these following notes. Okay, so our job is first to find what all these parameters and then substitute into the equations to get what is the bearing resistance per plate. So here is the FBRD, and as you can see just now, I have copied the formula. Okay, and then we need first to find what is alpha B. So in the given clauses, alpha B is equivalent to minimum of either E1 over 3D naught or FUB over FU or 1. Therefore, D naught is equivalent to 22, so you substitute D naught. You know what is your FUB and FU, substitute, and then you calculate, you get the minimum of 0.61, 1.86 and 1.0. So you need to determine what is the minimum. So in this case, the minimum numbers of these three value is 0.61. Therefore, alpha B is equivalent to 0.61. So here you can now have, you already find what is your alpha B, which is 0.61. So now let's find the other parameter, where actually you already know what is your FU. You need to find your D and your T. So since all the other parameter is quite easy and straightforward for you to find, let's now find what is K1. Again, in the equations, it's given to you the K1 is the minimum of either 2.8 E2 over D naught minus 1.7 or 1.4 P2 over D naught minus 1.7 or 2.5. Again, substitute all the required equations into the given parameter, and in this case, I'm sure some of you will ask the questions whereby, because earlier we have checked that P2 is not within the allowable requirement. Okay, so supposingly P2 need to be increased to 53 millimeter. However, in these questions, we just go through and check according to the proposal of the structural connections arrangements. And once we have checked all the necessary verifications, therefore after that we will do the necessary changes based on the new structural configurations. But in this case, we maintain by calculating the value of 50 by substituting P2 equals to 50. Alright, so here you can see when you substitute, and the minimum between here, here and here, we can know that 1.48 is the minimum value, and therefore K1 is equivalent to 1.48. And substitute all the parameters that we have calculated earlier, we get 82 kilonewton, which is larger than 37.5 kilonewtons of the shear force or bearing capacity for each of the bolts. Okay, and here there are some notes. Okay, the aggregate thickness of the outer plates, T outer, is larger than T inner. Okay, so here in this case, you can see 1.48, alright, times with 0.61. Okay, this is your alpha B. FU is your 430, and 22 is the diameter bolt, diameter hole of your thickness of your bolt, and 12 mm is the thickness of your plate. So to calculate the bearing capacity, we take note that the aggregate thickness of the outer plate, which is the outer plate is 8 mm, which is larger than the inner plate, which is 12 mm. Since the outer is larger than 12 mm, okay, so since the outer is lesser than the inner plate, therefore you need to take the thickness of the inner plate, which is 12 mm, and you get 82 kilonewton. So here we can say that in terms of the bearing capacity, the proposed arrangement is satisfied as it is larger than 37.5 kilonewton.
Okay, now let's continue with the next questions. So next questions requires us to check the load capacity of the connections with respect to bolt to block tearing. So basically for block tearing, I have give you the examples in the previous videos. So the concept block tearing that we have learned in the previous videos applied in these questions. So let's look how the block tearing going to occur for these particular examples. Okay, as you can see here, this is the three-dimensional illustrations for the bolt in these examples. As you can see, we have 150 kilonewton came from these directions, which is pull the inner plate, which is 12 millimeter thickness, and therefore the balance is 75 kilonewton. We'll pull the top and bottom, which is each of it is 8 millimeter thickness. So when this happens, as you can see in the block tearing video, okay, you can see that when 150 kilonewton being pulled, some portions of the plate will damage, or they will crack, and the line of crack will follow the bolt rows. And here are the examples. Okay, here are the examples how the block will be teared off from the inner plate. So if you can see, this is the block which is has been pulled out, and this is the remaining block. In this case, the load is considered as concentrically loading. So for concentrically loading, you need to know what is the main equations. This is the main equations for the concentrically loading, where you need to have Fu ANT 1 over square root 3 Fy ANV, gamma M2, gamma M0. So the rest of these parameters is straightforward, where we can have it in all the documents given in these examples. However, ANT and ANV are the one that you need to calculate. In these examples, you may get directly how to calculate that, but my intention here is that I don't want you to memorize the equations, but what I want you to do is to understand how to calculate the ANT and ANV. Let's refer to these diagrams. As I said earlier, ANT is the area which is perpendicular with the load applied. So the load applied is from this direction, which is 150 kilonewton. So the area which is perpendicular with this direction is the one that shaded in red color. okay, the one shaded in the red color. So those areas are considered as the area intentions, OA and T. So to get this area, I have highlighted equations because you have E2 times with the thickness, okay, but here you need to deduct the D naught area, which is the D naught area. E2 is measured from the center, okay, E2 is measured from the center of the bolt to the end edge. So since the half of the bolt has been taken out like this, okay, so therefore the remaining plate must be deducted with the D naught divided by 2, okay. So E2 minus, okay, D naught divided by 2, therefore you now get you need to multiply with 2, because here also E2 minus D naught divided by 2 and multiply with T. So the total A and T is supposed to be the total, okay, total A and T must be multiplied with 2, because you have 2 area which is acting under tension here. And the other area which also acting under tension is this area, which is in the different line of actions. Here they are in the same line of actions, but here is a little bit far away from this line of actions. So the area A and T here is calculated by having P2 minus D naught times T. Why P2? P2, okay, minus D naught, because we have 2 whole area here, okay, which you need to minus with the D naught, and half D naught here plus half D naught here, it's become D naught, so times with the thickness. So here is the area where P2 minus half D naught, which minus with D naught, which is half plus half, become 1, and times with T, which is the thickness. So therefore you get A and T, P2 minus D naught times T. And another interesting area that you need to find is the shear area, which we call as A and V. So if A and T is the one perpendicular to the load applied, whereby shear is always the area parallel to the load applied. So this is the load directions, okay, therefore here are the one which is shaded in blue color is the one what we call as A and V. So you don't need to memorize, you need to know which are the area. So here A and V, okay, equivalent to, you have E1 plus P1, but you need to minus with 1.5 D naught, because here you have 1 D naught and here you get half of it, okay, half of the D naught. So total length minus half D naught, okay, so therefore you times with T, and then you get A and V. Again you need to multiply by 2, because there are 2 shear area for this particular block tearing cases. Therefore in this case also you need to multiply by 2. Having go through the illustration diagrams, so let's now we insert all the formulations into the equations. So we now know that our E2 is 40 minus our D naught is 22, so 22 divided by 2. Finally we get 696 when you have multiplied with 2, and the reason why you multiply by 2, as explained earlier, the area of A and T in this particular phase are 2, so that's why you need to multiply by 2. But here, okay, you have A and T equivalent to P2 minus D naught times T, which is the area here, okay, the area here. But you don't need to multiply by 2 because it's only have one area here, alright, and therefore you get 336 millimeter squared. So here you might have a questions. You have 2 A and T. Do we need to add them, or how. In these particular examples, because you have two A and T, okay, the first one which came from these two, and the second one is come from this, and you need to compare which of the tensile area will give you the least value. So here the first one you get 696 millimeters squared, and the second one is 336 millimeters squared. So therefore in this case we choose the minimum value where A and T is equivalent to 336 millimeters squared. So then we're done for A and T. So now let's go for A and V. So if you can see for A and V, the equation has been derived and has been illustrated earlier, as you can see in this diagram, where I have highlighted that the shaded blue color is for the A and V. Okay, and you need to multiply by 2 because there are two of the A and V area, which is the shear area. So once you get that, okay, once you get those A and V, so A and V in this particular case, you just need to insert the data P1, E1, and D0, whereby you get 1368 millimeters squared. So while having the A and V and A and T, therefore we can now solve the block theory equations by inserting all the data that we have into the formulation given in the Euro codes, substitute all the informations, and finally you have calculated and you get your block theory, which is 33 kilonewton, and this 333 kilonewton is larger than 37.5 kilonewton, which is the shear area for the bolt and also for the plate. So therefore it's considered okay. Okay, the last check that you need to carry out for our example is to check the load capacity of the connection with respect to the plate tension capacity. To recall, you need to look at this slide where the tension capacity, the resistance of the tension capacity for a connections is represented by the least value between NPLRD and also NURD, okay, whereby NPLRD is assumptions that we made if we pull the plate and it is not fail at any row of the bolts, okay, but NURD is the one that we need to analyze by assuming that there is a failure occurs through the bolts area. So in this case, to find NPRD is very straightforward, where you just get the area, which is 130 times 12 times 275 divided by 1, you get 429 kilonewton. While for the NURD, which is ultimate resistance design, in this case you use 0.9 A net times FU over gamma M2, and then your A net, okay, your A net is 130 minus 2 times 22, okay, times 12, and then you get this is 275 divided 1.25, and finally you get 204, and 204 compared to 429, the ultimate resistance is much lower. Therefore the resistance capacity of your bolt is 204, and 204 is larger than 37.5 kilonewton, which is considered okay. Alright, there might be someone will ask or will not really clear how does this value come from. Alright, so let me show you how you can cut why it is 130 minus 2 times 22 and times 12, and this is actually the way how you calculate the A net. Okay, so the A net for the gross cross-sectional area, if you can see these diagrams, So let's look at the cross sections from here, putting your eyes here. Okay, if you're putting your eyes there, you will get, let's see, this is okay, and the plate thickness is 12 mm, which is in the middle. Okay, 12 mm, and then you have two bolt. Okay, you have two rows of bolt. All right, so you have two rows of bolts in particular dimension. So in this particular case, your length is 130 millimeter. So here is diameter bolt, which is 22, and here is 22. So for you to get the net area, which is the one which is not being shaded, is 130 mm. Okay, 130 minus with 22 times 12. Okay, but you need to multiply with 2 because they are 2. So this is what is your area net, and the same you apply here. Alright, and when you apply it there, so therefore you get 204. So by calculating all these equations, whereby in this example, just to summarize, okay, in these examples, what we can summarize is that in terms of the configurations of this bolt, the edge distance for P2, okay, P1, you can see the minimum and maximum edge distance is fine, okay, and the what we call it, the P1 is fine, but the P2 we have some problems, not okay. Therefore you need to adjust the structural configuration for these connections because it is less than 50:8. So meaning that for P2, so this value, okay, you need to increase because the allowable is 53 mm. So at least you need to increase to 53 mm, the correction that we have to do for this double lap joint. And secondly, in terms of the evaluations with these particular examples, in terms of bolt shear, okay, it is pass. In terms of bolt bearing, also pass. And then block tearing also pass, and plate tension capacity is also pass. So in these examples for double lap joint, everything's satisfactory except from the P2. So that is the comment for example 2. So next examples is a typical examples. So for the first example, which is single lap joint, this example single lap joint, for this one I would like you to try on your own because this is the basic examples. Okay, this is the basic examples where you can try on your own, because I have complete for the harder one, which is double lap joint. So you need to watch the next examples. Thank you.